Right now, you're standing inside something 0 light years wide, about 0 trillion miles of stars, gas and dust, rotating in a slow cosmic dance. This is the Milky Way. Everything you've ever known, every human who ever lived, every civilization, every moment of history exists inside this single spiral of light. And we're about to leave it. We'll begin here, in our home galaxy, then push outward into the darkness beyond. First, we'll discover that the Milky Way isn't alone. Then we'll encounter forces dragging entire galaxies through space at unimaginable speeds. And eventually, we'll reach a boundary where the universe itself refuses to reveal anything more, a horizon beyond which light can no longer reach us. If you're ready to travel across 2 trillion galaxies and see what truly lies out there, now's the time to join the journey. Here's the thought that bends your mind. If you could fly through the observable universe, visiting every galaxy along the way, our home would account for just 0.000000005% of the trip. A single flicker of light in an ocean of darkness, yet somehow, it's where everything that ever mattered to us began. We're about to take that journey. We'll start here in our galaxy, then push outward into darkness. First, we'll discover we're not alone. Then, we'll find something pulling us through space at impossible speeds. By the end, we'll reach a wall where the universe itself stops letting us see further. And along the way, everything you thought you knew about space, time, and reality will completely fall apart. If you're ready to fly through 2 trillion galaxies and see what's really out there, hit that like button and subscribe. This is going to take over an hour. Get comfortable. Picture this. You're floating above Earth, looking down at the blue marbles spinning below. Now you start flying. Not rocket speed, not even light speed. You're moving at light speed. 186.0 miles every single second. Fast enough to circle Earth 7 times in 1 heartbeat. You pass the Moon in 1 second, Mars in 4 minutes. You blow past Jupiter, that massive gas giant, in 35 minutes. Neptune takes 4 hours. And then you're in the dark, the real dark, the space between our star and the next closest star. You fly for 4 years straight through absolute nothing before you reach Proxima Centauri. 4 years at the speed of light, just to visit our nearest neighbor. But you keep going. You pass thousands of stars, tens of thousands, each one burning with its own family of worlds, most of which we'll never see, never know, never understand. You're flying through the spiral arm of the Milky Way now, weaving between stellar nurseries where baby stars are being born inside clouds of hydrogen gas so massive they'd swallow our entire solar system like dust. You pass red giants dying in slow motion, white dwarfs cooling into darkness, neutron stars spinning hundreds of times per second with magnetic fields that could rip iron from your blood from 1,000 miles away. 50 years pass. You're at the galaxy's edge. You look back and see it. The entire Milky Way laid out like a cosmic pinwheel, 400 billion stars spinning together in a spiral 200 light years across. The disk glows with blue young stars burning hot and fast along the spiral arms. The central bulge burns yellow-orange, packed with older stars. And in the very center, hiding behind clouds of dust, sits a black hole 4 million times more massive than our star, holding everything together with invisible gravity. Remember this moment. Remember how vast this feels, because in about 10 minutes you're going to discover that our entire galaxy is microscopic. Here's what nobody tells you about the Milky Way. It's not floating alone in empty space like some solitary island. We're bound to something. 54 galaxies orbit and dance together in a region astronomers call the local group. It stretches 3 million light-years across. Our galaxy and Andromeda are the 2 massive spiral galaxies, each containing hundreds of billions of stars. Then there are dozens of smaller dwarf galaxies, some with only a few billion stars caught in our gravitational net. And Andromeda isn't sitting still. Right now, at this exact moment, it's screaming toward us at 250 mph. In 4 billion years, these 2 galaxies will collide, not like 2 rocks smashing together, like 2 clouds merging. The stars are so far apart that almost nothing will actually hit anything else. But gravity will tear both galaxies apart and rebuild them into something new. A giant elliptical galaxy astronomers have already named Milkomeda. But here's what makes this insane. We're not just bound to these 54 galaxies. We're moving towards something else, something massive, something that shouldn't be possible. You've left the local group behind, 54 galaxies fading into the darkness as you push farther out. You've been flying for millions of years now, passing thousands of galaxy groups just like ours, each one containing its own collection of spirals, ellipticals, dwarf galaxies bound together by gravity. But something strange is happening. You're not alone out here. Every single galaxy around you, including ours back home, is moving in the same direction, not drifting, racing, 1.3 million miles per hour toward a single point in space, roughly 150 million light-years away. That's fast enough to cross the entire United States in 3 seconds. Astronomers discovered this in the 1970s. They mapped the motion of thousands of galaxies and found them all flowing like water down a drain towards something in the direction of the Centaurus and Hydra constellations. They called it the Great Attractor. Here's the problem. They couldn't see it when they pointed their telescopes at that region, the zone of avoidance. The disk of our own galaxy blocks the view with dust and gas. Whatever is pulling 100 galaxies, including our local group, remained invisible, hidden behind our galaxy's central bulge, like something lurking behind a curtain. Years later, better instruments pierced through the dust. They found it. Not a single object. A massive overdensity. Imagine a region of space where tens of thousands of galaxies pile up, their combined mass creating a gravitational well so deep that everything within 200 million light-years feels the pull. But that's not the strangest part. The Great Attractor itself is moving. Something even more massive, something even farther away is pulling the attractor. And that something is pulling everything around it. We're not just falling toward one destination. We're riding a current in a cosmic ocean we're only beginning to map. Remember that pull. Remember that we're passengers on a journey we didn't choose, moving towards something we still don't fully understand. Because what comes next makes the Great Attractor look small. Keep flying. You're 300 million light-years from home now. The Milky Way is gone. The local group is gone. Even the Great Attractor has vanished behind you into the darkness. And from this distance you can finally see what you're inside. A river. A cosmic river. In 2014, astronomers mapped the motion of 80 galaxies around us, not just their position, their velocity, which direction they're moving, and how fast. When they connected the dots, a pattern emerged. All those galaxies, including ours, flow along specific pathways through space like water, following channels carved into stone. They named it Laniakea, Hawaiian for immeasurable heaven. It stretches 520 million light-years across and contains 100 galaxies. The entire structure holds the mass of 100 quadrillion times our star. That's a 1 with 17 zeros after it. Picture it like this. Imagine you're looking at a map of river systems from above. You see tributaries merging into streams, streams merging into rivers, rivers flowing toward a central basin. That's what galaxies do. We're not scattered randomly through space. We flow. Our local group is one tributary. The Great Attractor is downstream from us. And everything converges toward a central basin called the Great Attractor Wall, a flat concentration of tens of thousands of galaxies stacked like dominoes. You're flying along one of these channels. Now, galaxies stream past you on all sides, all moving in roughly the same direction, all following the gravitational contours carved into space itself by invisible mass. Some channels carry hundreds of galaxies, others carry thousands. And this is just one supercluster. From here you can see others. Shapley supercluster sitting 500 million light-years away, pulling on everything around it with even more mass than Laniakea. Perseus Pisces supercluster in another direction. Coma supercluster beyond that. Each one containing tens of thousands to hundreds of thousands of galaxies, each one a river system in its own right, But here's what changes everything. These rivers don't flow through empty space. They flow through something, a structure, a web. You pull back farther, 1 billion light-years from home, then 2 billion, then 5 billion. And from this distance the pattern becomes impossible to miss. Galaxies don't fill the universe evenly. They cluster into superclusters. The superclusters line up into vast filaments, threads of light millions of light-years thick and hundreds of millions of light-years long. These filaments connect at nodes where superclusters pile up. Between the filaments, you see walls, sheets of galaxies stacked flat like cosmic membranes. Some walls span 500 million light-years across, but measure only a few million light-years thick. This is the cosmic web, the skeleton of the universe. Every galaxy you visited, every star you've passed exists somewhere on this web, following the threads and walls like cities built along highways. And between the threads, between the walls, you notice something else. Darkness. Not the normal darkness of space. Something emptier. Something vast. These are the voids, and they're about to redefine what you think empty means. You turn away from the filaments and dive into a void. The galaxies vanish. Not slowly, not gradually. You pass the last filament and suddenly there's nothing. You fly for 10 million light-years. Nothing. 20 million light-years. Still nothing. 50 million light-years of pure empty space stretching in every direction. No galaxies, no stars, no gas clouds, no dust. Just you and the darkness and the faint glow of the cosmic web surrounding this empty bubble like cage bars miles away. This is the Botez void, also called the Great Nothing. It spans 330 million light-years across. If the Milky Way sat at the center of this void, we wouldn't see another major galaxy for 165 million light-years in any direction. The nearest stars would be so far away that their light would take longer to reach us than dinosaurs have been extinct. About 60 galaxies exist inside this void. In a normal region of space this size, you'd find 0. The void is 97% empty. Now imagine this. Voids like Botez aren't rare. They're everywhere. They make up roughly 80% of the universe's volume. Most of space is nothing. The cosmic web, all those filaments and walls, all those superclusters and galaxies and stars, they're the exception, the minority. You could fit thousands of Milky Ways inside a single void, and they'd never see each other. The Eridanus supervoid, the CMB cold spot void, the giant void, the Capricornus void, each hundreds of millions of light-years across, each one containing almost nothing. Some are so empty they create cold spots in the cosmic microwave background, the afterglow of the Big Bang itself, because so little matter sits in these regions to emit heat or radiation. Scientists still don't know exactly why voids form. The leading theory says gravity created them. In the early universe, matter distributed almost evenly across space, but not perfectly evenly. Tiny fluctuations, quantum ripples from the Big Bang, meant some regions had slightly more matter than others. Gravity amplified those differences. Dense regions pulled in more matter, growing denser. Sparse regions lost matter, growing emptier. Over billions of years, matter evacuated the voids and piled up along the edges, forming the filaments and walls of the cosmic web. The voids expanded. They're still expanding, getting emptier, growing larger. In 1 trillion years, the voids will dominate even more than they already do. You exit the Botez void and return to the web. The filaments blazing with galaxies feel crowded now. After that emptiness, you realize something profound. The universe isn't about the light, it's about the darkness. The galaxies, the stars, everything we see, it's just scaffolding wrapped around nothing. But that scaffolding isn't stable. Those galaxies aren't permanent, because almost everything out here is colliding with something else. And that includes us. 250, 0 mph. That's how fast Andromeda is approaching our galaxy right now. While you read this, the two largest galaxies in the local group are closing the gap, pulled together by gravity's patient hand. In 4 billion years, the collision begins. First, the outer edges touch. Stars from both galaxies intermingle like two swarms passing through each other. Most stars won't hit anything. The distances between them are too vast, but gravity tears both galaxies apart. Spiral arms shred. The disks warp and distort. Gas clouds collide and ignite, birthing millions of new stars in violent blue bursts across both galaxies. The galactic cores approach each other. Two supermassive black holes, one 4 million times our star's mass, the other 100 million times our star's mass, spiral inward on a collision course. They'll orbit each other for 1 million years, getting closer with each pass, radiating gravitational waves that ripple through space-time itself. Then they merge, two black holes becoming one. The resulting supermassive black hole, 104 million times our star's mass, sits at the heart of a new galaxy. Not a spiral, an elliptical, a football-shaped swarm of stars with no disk, no arms, just a chaotic ball of orbits. Milkomeda, part Milky Way, part Andromeda, all collision. Now multiply that story by trillions. You're flying through the universe, watching galaxies collide everywhere. The antenna galaxies, two spirals locked in a 100 million year merger, their cores glowing bright as gas compresses and stars form by the millions. The mice galaxies, named for their long tails of stars ripped free by tidal forces. The tadpole galaxy with a tail 280 light-years long, drawn out like taffy by a smaller galaxy that punched through its disk. Most collisions don't look dramatic from the outside. No explosions, no debris fields, just two clouds of stars interpenetrating over hundreds of millions of years, reshaping each other through gravity. But the results transform everything. Spiral galaxies with elegant arms become elliptical blobs. Gas gets shocked and compressed, triggering starbursts, brief periods where a galaxy forms, stars hundreds of times faster than normal. Sometimes the collision funnels gas into the central black hole, igniting a quasar, an active galactic nucleus so bright it outshines the entire galaxy and can be seen from billions of light-years away. Stephan's Quintet. 5 galaxies locked in a gravitational dance. 4 of them are colliding in slow motion while a 5th sits in the foreground, unrelated but appearing in the same patch of sky. Their interaction has lasted hundreds of millions of years. It will continue for hundreds of millions more. And it gets worse. Galaxy clusters collide too. The Bullet Cluster. 2 massive galaxy clusters, each containing thousands of galaxies, pass through each other at millions of miles per hour. The galaxies themselves mostly survived, passing like ghosts through ghosts. But the hot gas between the galaxies, the intergalactic medium, didn't pass through. It collided. It piled up between the clusters in a shockwave, so hot it glows with X-rays. This is normal. This is what the universe does. Gravity builds structure, then gravity smashes it together. Nothing stays still. Nothing is safe. Every galaxy you've seen on this journey is either colliding now, will collide in the future, or is the product of past collisions. But here's something stranger than collision. The farther you fly from home, the deeper you travel into something even more impossible. You're traveling backward through time. Stop for a moment. Let's pull back and look at what we've discovered so far. We started in the Milky Way, 100 light-years across, 400 billion stars. It felt massive. Then we found the local group, 54 galaxies bound together, stretching 3 million light-years. The Milky Way became small. Then came the pull. The great attractor dragging 100 galaxies toward a single point at over 1 million miles per hour. We discovered we're passengers on a journey we can't control. We zoomed out farther and found Laniakea, 520 million light-years of cosmic river. 100 galaxies flowing along gravitational channels like water following ancient riverbeds. And Laniakea isn't alone. It's one supercluster among thousands, all following the same pattern. Then we saw it, the cosmic web. Filaments and walls of galaxies threading through space, connecting at massive nodes, forming a structure so vast it makes superclusters look like cities on a highway system. And between the threads, we found the voids. Enormous bubbles of almost nothing spanning hundreds of millions of light-years. 80% of the universe is empty space. Finally, we watched galaxies collide, not occasionally, constantly, everywhere, including our future collision with Andromeda in 4 billion years. The universe builds structure through gravity, then smashes it together, then builds something new from the wreckage. Here's the pattern. Scale is an illusion. Every time we think we've seen something huge, we pull back and discover it's tiny. Every time we think we understand the structure, we zoom out and find a deeper layer. The universe is nested. Galaxies nest inside groups. Groups nest inside clusters. Clusters nest inside superclusters. Superclusters line up into filaments. Filaments form the web. And between everything sits darkness. But there's another pattern emerging, something we haven't addressed yet. Something that breaks physics. Every galaxy you've seen so far exists right now, present tense. When you look at a galaxy 1 million light-years away, you're seeing light that left that galaxy 1 million years ago. The galaxy has moved, changed, evolved since then. You're seeing its past, not its present. The farther you fly, the farther back you look. At 1 billion light-years, you see 1 billion years into the past. At 5 billion light-years, you see the universe when it was 5 billion years younger. And when you reach the edge, when you fly as far as light allows, you'll see something no galaxy should survive. You'll see the universe being born. Let's keep flying. Here's what nobody tells you about flying through space. Distance and time are the same thing. Light travels at 186.0 miles per second, finite speed. That means when you look at anything, you're seeing the past. The moon is 1 light second away. You see it as it was 1 second ago. Our star is 8 light minutes away. The light hitting your eyes right now left its surface 8 minutes ago. If our star exploded, we wouldn't know for 8 minutes. Proxima Centauri, the nearest star, sits 4 light-years away. The light you see tonight left that star 4 years ago. If it died 3 years ago, it's still shining in our sky, a ghost broadcasting its own obituary on a 4-year delay. Now, scale that up. You're flying through space, passing galaxies. A galaxy 10 million light-years away. You're seeing it as it existed 10 million years ago when our ancestors were still learning to walk upright on African plains. A galaxy 100 million light-years away. You're seeing the age of dinosaurs frozen in starlight. A galaxy 1 billion light-years away. You're watching it from a time before complex life existed on Earth. The farther you fly, the farther back you see. Every additional light-year is another year into cosmic history. You're not flying through space anymore, you're flying through time. At 1 billion light-years, galaxies look different. More irregular, more chaotic, fewer grand spirals, more collisions in progress. The universe was younger then, more violent, still settling into structure. At 5 billion light-years, you see the universe at middle age. Our star hadn't formed yet. The Milky Way was smaller, still accumulating mass from smaller galaxies. Star formation rates across the universe were higher, more gas available, more raw material for building stars. At 10 billion light-years, you're watching the universe in its youth. Galaxies are smaller, less massive. Many are irregular blobs without clear structure. The cosmic web is there but less defined. Voids are smaller. Filaments are narrower. Everything is more compressed. And you keep flying, 12 billion light-years. The universe is only 2 billion years old here. Galaxies are primitive. Most are dwarf galaxies. Small collections of stars just beginning to merge into larger structures. The first quasars blaze in the darkness. Supermassive black holes gorging on gas and outshining entire galaxies. 13 billion light-years. The universe is barely 1 billion years old. You're approaching the cosmic dawn, the period when the first stars ignited and began burning away the neutral hydrogen fog that filled all space after the Big Bang. Before this moment, the universe was dark. Literally dark. No stars existed, just hydrogen and helium cooling in the darkness. And then you see something impossible. A galaxy fully formed, massive, organized, spiral structure clearly visible, stars burning in orderly patterns. It's detailed and mature and complex, but according to every model, every simulation, every physics equation we have, this galaxy shouldn't exist yet. The universe at this distance is only 300 million years old. That's barely enough time for the first stars to form, let alone entire galaxies. You need time for stars to form, time for those stars to die and scatter heavy elements, time for those elements to collect into new stars, time for gravity to organize millions of stars into rotating disk structures, time that doesn't exist here. Yet here it is, Jade's GSZ 40, a galaxy containing hundreds of millions of stars, beautifully structured, existing when the universe was still a cosmic infant. And it's not alone. They keep appearing. Massive galaxies in the early universe. Galaxies that break every rule about how long structure takes to form. Glass Z, a galaxy observed just 300 million years after the Big Bang. It contains 1 billion stars. 1 billion. Each star needed time to form, time to gather gas, time to ignite fusion, time to live and die and create the next generation of stars. Cosmologists estimated this process should take 1 to 2 billion years minimum. This galaxy did it in 300 million. SPT 31158, a massive elliptical galaxy observed when the universe was 1.4 billion years old. Elliptical galaxies form from mergers. Multiple spiral galaxies have to collide, intermingle, lose their disk structure, and settle into a football shape. That's a multi-billion-year process involving several separate galaxies, each taking billions of years to form first. This galaxy did all of it in 1.4 billion years. The pattern keeps repeating. Astronomers find mature galaxies at redshift 7, 8, 10, 14. Each number represents looking farther back in time. Each one shows galaxies that shouldn't be possible yet, not that mature, not that massive, not that organized. Remember when I said the universe's age is 14 billion years? That number is about to stop making sense. The James Webb Space Telescope has found hundreds of these early galaxies. Each discovery pushes the boundaries of what should be possible. Some contain supermassive black holes at their centers, black holes millions of times more massive than our star. Those black holes also shouldn't exist yet. They need time to grow, time to accrete mass, time to evolve from stellar black holes into supermassive monsters. One theory says dark matter. Maybe dark matter clumped together faster than we thought, creating deeper gravitational wells earlier in cosmic history, accelerating the galaxy formation process. Maybe the first galaxies formed in dark matter halos so dense that star formation happened at rates we've never seen in the modern universe. Another theory says our cosmological models are wrong. Maybe the universe went through a period of rapid structure formation we don't understand. Maybe the physics of the early universe worked differently than they do now. Maybe constants we think are constant actually change over cosmic time. Or maybe, just maybe, something even stranger is happening. These galaxies are real. The telescopes don't lie. The light traveled billions of years to reach us. The redshift measurements are accurate. The distance calculations are sound. So either our entire understanding of cosmic evolution needs revision, or the early universe was far more efficient at building galaxies than we ever imagined. And that's not the only thing breaking our models, because while you've been flying for 13 billion light years, covering 13 billion years of cosmic history, something impossible has been happening to the universe itself. It's been expanding, not just expanding, accelerating. Space itself is stretching, pulling galaxies apart faster than light can travel between them. Which means the galaxy you're looking at, the one 13 billion light-years away that you're seeing from 13 billion years ago, it's not 13 billion light-years away anymore. It's 46 billion light-years away right now in the present. Wait. How can the universe be 14 billion years old, but contain objects 46 billion light-years away? How can something travel 46 billion light-years in 14 billion years? Because space doesn't follow speed limits. Space can expand faster than light, and it has been since the beginning. Let's break physics for a moment. The universe is 14 billion years old. Light has been traveling for 14 billion years maximum. Therefore, the farthest we should be able to see is 14 billion light-years away. Simple math. Except the observable universe is actually 93 billion light-years across, 46 billion light-years in every direction from Earth. That's impossible unless you understand what expansion means. Space itself is expanding, not galaxies moving through space. Space stretching. Imagine dots on the surface of a balloon. You inflate the balloon. The dots don't move. The rubber between them stretches. The distance between dots increases even though the dots stay put. That's what's happening to the universe. Now, here's the trick. There's no speed limit on how fast space can expand. Einstein's relativity says nothing can move through space faster than light. But space itself, space can do whatever it wants. In the early universe, space expanded incredibly fast. During inflation, a period less than 1/1,000,000,000 of a trillionth of a trillionth of a second after the Big Bang, space expanded by at least a factor of 10 to the 26th power. The entire observable universe inflated from smaller than an atom to the size of a grapefruit in less time than it takes light to cross a proton. After inflation ended, expansion continued but slowed down. For the first several billion years, gravity fought against expansion, trying to pull everything back together. Expansion won, but barely. Then, about 5 billion years ago, something changed. Expansion started accelerating, getting faster. Galaxies began moving apart from each other at increasing rates. We call this force dark energy. We have no idea what it is. It makes up 68% of the universe's total energy density, and it's pushing space apart from within. The farther apart 2 points in space are, the more dark energy exists between them, the faster they separate. This is why a galaxy 13 billion light-years away in light travel time is actually 46 billion light-years away in present distance. While that light was traveling toward us for 13 billion years, space expanded. The galaxy moved farther away, not because it's moving through space, because space itself stretched, carrying the galaxy with it. Picture it like this. You're on a moving walkway at an airport, walking towards someone at the other end. But the walkway is stretching as you walk. You're moving forward at your walking speed, but the distance between you and the other person is increasing faster than you can walk. You're making progress. Your light is traveling, but the finish line keeps getting farther away. Now, scale that up to cosmological distances. A galaxy 46 billion light-years away right now is receding from us faster than light. Not moving faster than light through space, but being carried away by space expanding faster than light can cross it. The light leaving that galaxy right now will never reach us ever. Space will expand too fast for the light to make any progress. We call this the cosmological horizon. Beyond 46 billion light-years, galaxies exist that we can never see. Not with better telescopes, not with infinite time. They're beyond the edge of the observable universe, separated from us by space expanding faster than information can propagate. But here's what keeps cosmologists awake at night. The acceleration is increasing. Dark energy is pushing harder. In the far future, billions of years from now, even nearby galaxies will recede beyond our horizon. The local group will stay bound together by gravity, but everything else will vanish. Future civilizations will look at the sky and see almost nothing. No distant galaxies, no cosmic web, just the local group surrounded by infinite darkness. They'll think they're alone in the universe, and they'll be right. Not because nothing else exists, but because expansion has hidden everything beyond an ever-shrinking horizon. Speaking of hidden things, most of what you've been flying through doesn't actually exist in the way you think it does. Remember when I said something invisible was pulling us? The great attractor? That wasn't quite true. The mass isn't invisible. The matter creating that mass is dark matter. 85% of all matter in the universe doesn't interact with light, can't be seen, can't be touched, can't be detected directly. It doesn't emit radiation, doesn't absorb radiation, doesn't reflect radiation. It only interacts through gravity. Every galaxy you've passed on this journey, including ours, sits inside a halo of dark matter 5 to 10 times more massive than all the visible matter combined. Picture the Milky Way's 400 billion stars. All its gas and dust, everything we can see. Now, multiply that mass by 5. That's how much dark matter surrounds our galaxy in an enormous sphere stretching far beyond the visible disk. We discovered this in the 1970s. Astronomer Vera Rubin measured how fast stars orbit in spiral galaxies. Basic physics says stars farther from the galactic center should orbit slower, just like outer planets orbit our star more slowly than inner planets. But they don't. Stars at the galaxy's edge move just as fast as stars near the center, sometimes faster. That's impossible unless there's additional mass we can't see. Mass spread throughout and beyond the galaxy, contributing to gravity, pulling on those outer stars and speeding them up. Dark matter. Every galaxy has it. Every cluster has it. The cosmic web is scaffolded by dark matter filaments. Visible matter simply traces where dark matter already sits. The bullet cluster proved it. Remember when I mentioned two galaxy clusters colliding? The visible galaxies passed through each other. The hot gas between them collided and piled up. But when scientists measured the gravitational lensing, the bending of light by mass, they found most of the mass hadn't piled up with the gas. It had passed straight through. Just like the galaxies, dark matter doesn't interact with normal matter at all. Two dark matter particles can pass through each other like ghosts. They only interact through gravity. So when the clusters collided, the dark matter halos passed through each other, separating from the visible gas, proving they're made of something completely different. We don't know what dark matter is. Leading candidates include WIMPs, weakly interacting massive particles, theoretical particles that have mass but almost never interact with normal matter, or axions, extremely light particles created in the early universe, or primordial black holes formed in the first fractions of a second after the Big Bang, or something else entirely that we haven't imagined yet. But here's what we know for certain. Without dark matter, galaxies wouldn't exist. The visible matter alone doesn't have enough gravity to hold galaxies together. Stars would fly apart, spiral arms would dissolve, galaxy clusters would evaporate. The cosmic web would never have formed. Structure requires dark matter. In the early universe, dark matter clumped first. It created gravitational wells. Normal matter, hydrogen and helium, fell into those wells. Once enough normal matter collected, it compressed, heated up, and ignited into stars. Galaxies formed where dark matter told them to form. You're not flying through a universe of stars and galaxies. You're flying through an ocean of invisible matter. Everything you see, every light source, every star and galaxy, it's foam on the surface of a dark ocean, billions of light years deep. And that ocean is pushing you towards something. The edge, the wall, the place where we can't see any farther. Not because nothing exists beyond it, but because the universe won't let us look. You've been flying for 13.8 billion years now. That's almost the entire age of the universe. You've watched galaxies evolve backward, seen the cosmic web grow simpler, observed the void shrink. You're approaching cosmic dawn, the moment when the first stars ignited, but you push farther. 13.9 billion light years, 14 billion light years. The galaxies vanish. Not gradually, suddenly, like someone flipped a switch. You're surrounded by an orange glow, not from stars, from hydrogen. Neutral hydrogen gas filling all of space, cool enough that it doesn't emit visible light, but warm enough to glow faintly in the infrared. This is the Dark Ages, the period after the Big Bang, but before the first stars. Hydrogen and helium gas cooling in the darkness, slowly clumping under gravity, preparing to form the first generation of stars. No light exists here, except the faint afterglow of creation itself. You fly farther still, 14.1 billion light years, 14.3 billion light years. The orange glow gets brighter, hotter. The temperature is rising as you move backward through time. The hydrogen begins glowing brighter, shifting from infrared to red to orange to yellow, 14.7 billion light years. The glow becomes a wall of light so intense you can't see past it. The cosmic microwave background. The oldest light in the universe. 13.8 billion years ago, the universe was hot, ridiculously hot. a dense plasma of protons, electrons, and photons, all crammed together, colliding constantly. Light couldn't travel through this plasma. Any photon that tried to move forward immediately collided with an electron and scattered in a random direction. The universe was opaque, foggy, thick with matter and radiation mixed together. Then 380 years after the Big Bang, the universe cooled enough. Electrons and protons combined to form neutral hydrogen atoms. The fog cleared. Photons could finally travel freely through space without constantly hitting electrons. The universe became transparent for the first time. Those first free photons are what you're seeing now, the cosmic microwave background. Light that has been traveling for 13.8 billion years from every point in space. It started as visible light, bright orange, the color of cooling metal. But as space expanded, the light stretched with it. The wavelength increased. Orange became red. Red became infrared. Infrared became microwave. Today, the CMB has a temperature of only 3 degrees above absolute zero. This wall of light marks the surface of last scattering, the place and time when light decoupled from matter. You cannot see past it, not because nothing exists beyond, but because before this moment, the universe was opaque. Light didn't travel. It scattered constantly through the plasma fog. Trying to see past the CMB would be like trying to see past the surface of our star. You can't look into our star's interior because light can't escape from there. It's too dense. Photons scatter too many times before reaching the surface. Same principle here, but scaled to the entire universe. This wall sits 46 billion light-years away in every direction, a sphere surrounding us, the edge of the observable universe. Not the edge of the universe itself, just the edge of what we can possibly observe. But even this wall has structure, patterns, ripples that tell a story. Look closely at the CMB wall. It's not uniform. Tiny temperature variations ripple across its surface. Most of the sky glows at 2.725 Kelvin, but some patches are 2.724 Kelvin, others are 2.726 Kelvin. Differences of 1/10th of a degree. These ripples are fossils, quantum fluctuations from the Big Bang, amplified by inflation, frozen into the fabric of space as tiny density variations. Regions slightly hotter than average had slightly more matter. Regions slightly cooler had slightly less. Those tiny differences, microscopic variations in density, became everything. The hotter spots, the overdense regions, attracted more matter through gravity. Over billions of years, matter accumulated there. The first stars formed in those regions, then galaxies, then clusters, then superclusters, then the filaments of the cosmic web. The cooler spots, the underdense regions, lost matter. They became the voids. The structure you flew through, the entire cosmic web, was predetermined by these ripples. The pattern was set 380 years after the Big Bang. Everything that happened afterward, every galaxy that formed, every star that ignited, every structure that evolved, it was following a blueprint written in the CMB. Scientists have mapped this blueprint with incredible precision. The WMAP satellite, the Planck satellite, they measured the CMB temperature variations across the entire sky to 1 part per million. The maps reveal a story. The universe's geometry is flat, not curved, not like the surface of a sphere where parallel lines eventually meet, flat like a plane extending infinitely in all directions. This tells us the total energy density of the universe equals the critical density exactly, 100%. Any less and the universe would be open, curved like a saddle. Any more and it would be closed, curved like a sphere. The universe is 68% dark energy, 32% matter. Of that matter, 85% is dark matter, 15% is normal matter. The atoms that make up stars, planets, and us, we're 4.9% of the universe's total energy budget. 4.9%. Everything else is dark. The universe began in a hot, dense state 14 billion years ago. Not from some external cause, just began. Space-time itself began. Before the Big Bang, before, is a meaningless concept because time didn't exist yet. Asking what came before the Big Bang is like asking what's north of the North Pole. The question doesn't make sense. Inflation happened. The universe expanded by an enormous factor in a fraction of a second. This solved several problems. Why is the universe so uniform, so similar in all directions? Because regions that seem far apart today were actually in contact before inflation stretched them apart. Why is the universe flat? Because inflation stretched it flat, like inflating a balloon until the surface looks perfectly flat to any small observer. And those quantum fluctuations, they're why the universe isn't perfectly smooth, pure quantum randomness. Fluctuations in energy at the smallest possible scales got amplified by inflation to cosmic scales. They became the seeds of all structure. Everything you see, including yourself, traces back to quantum noise in the first trillionth of a second. The CMB also reveals what the universe will become. Dark energy dominates, expansion is accelerating, the cosmic web will gradually spread apart, stars will exhaust their fuel, black holes will evaporate through Hawking radiation. In 10 to the 100 years, the universe will be cold, dark, and essentially empty. Individual particles separated by distances larger than the observable universe is today, alone in the void, unable to interact with anything ever again. But that's trillions of years away. For now, the universe is alive, vibrant, full of stars and galaxies and structure. You've reached the edge, the wall, the place where observation ends. Let's turn around and see what this all means. You hover at the edge, facing the cosmic microwave background, then slowly turn around. The universe spreads before you. 46 billion light-years of structure visible in every direction. From here, you can see it all at once. The cosmic web in its entirety, filaments threading through voids, galaxy clusters glowing like city lights at intersections, the great attractor visible as a dense region pulling everything nearby, Laniakea stretching across 500 million light-years of space. The local group barely visible now, a faint collection of dots, and somewhere in that collection, the Milky Way. One galaxy among 2 trillion. You start the journey home, flying forward through time, watching the universe age instead of regress. The cosmic dawn happens in fast forward. The first stars ignite, supernova explode, heavy elements scatter. Second-generation stars form. Galaxies begin taking shape. Small dwarf galaxies merge into larger spirals. The cosmic web sharpens, filaments brighten, voids expand. You pass through 10 billion light-years. The universe looks more familiar now, more organized, more mature. The wild chaos of the early cosmos has settled into patterns. Spiral galaxies with beautiful arms, elliptical galaxies with smooth distributions, galaxy clusters with hundreds of members. At 5 billion light-years, you witness our star forming. A cloud of hydrogen and helium collapses under its own gravity in the Milky Way's disk. Temperature rises, pressure builds, fusion ignites. Our star begins burning, sending light into space for the first time. Around it, debris from the formation process clumps into planets, rocky worlds near the star, gas giants farther out, and one small blue planet in what astronomers will later call the habitable zone. At 1 billion light-years, Earth has cooled, oceans cover the surface. Simple, single-celled life is developing in those oceans, beginning the long process that will eventually lead to complex organisms, to consciousness, to civilizations that look up at the stars and wonder about their place in the cosmos. At 100 million light-years, dinosaurs walk the Earth while galaxies continue their collisions overhead, oblivious to the drama playing out on that small rocky world. At 10 million light-years, our ancestors are learning to use tools, to make fire, to communicate through language. The collision between the Milky Way and Andromeda is still 4 billion years away. But gravity has already locked the two galaxies together, sealing their fate. At 1 million light-years, humans have discovered agriculture, built civilizations, developed mathematics and science. They've begun asking questions about the cosmos. What are those lights in the sky? How far away are they? What is the universe made of? How did it all begin? At 100 light-years, you're back in the Milky Way, our home galaxy. The journey has come full circle. But you're different now. You understand what you're inside. Let's make sense of it all. Start with you. A human body contains roughly 7 octillion atoms. That's 7 followed by 27 zeros. Each atom is ancient. The hydrogen in your body formed in the Big Bang. The carbon, nitrogen and oxygen came from stars that died billions of years ago. The iron in your blood was forged in a supernova explosion. You are made of star matter. Literally, zoom out. You're standing on Earth, 80 miles in diameter, one of 8 planets orbiting our star. Our star is one of 400 billion stars in the Milky Way. The Milky Way is one of 54 galaxies in the local group. The local group is part of Laniakea. Laniakea is one supercluster among tens of thousands. The superclusters form the cosmic web. The cosmic web fills the observable universe. At each scale, what seemed large becomes insignificant. Your body is enormous to a cell. Earth is enormous to you. Our star is enormous to Earth. The Milky Way is enormous to our star. The local group is enormous to the Milky Way, and so on until you reach the cosmic web, which is enormous even to superclusters. But the cosmic web isn't the universe. It's just the part we can see, the observable universe. Beyond the CMB wall, beyond our 46 billion light-year horizon, the universe continues. How far? We don't know. Possibly infinite. Possibly just incomprehensibly larger than what we can observe. If the universe is infinite, then every possible arrangement of matter exists somewhere. An infinite universe contains infinite galaxies, infinite stars, infinite planets, infinite Earths with infinite versions of you reading infinite versions of this script. Statistical certainty in an infinite sample size. Even if the universe isn't infinite, it's at least 400 times larger than the observable universe based on measurements of cosmic curvature. That's a sphere roughly 20 trillion light-years across, containing more galaxies than our entire observable universe holds atoms. Now, think about time. The universe is 14 billion years old. Our star is 4.6 billion years old. Earth is 4.5 billion years old. Complex life emerged around 500 million years ago. Humans appeared roughly 300 years ago. Written history goes back 50 years. Your lifetime probably less than 100 years. In cosmic terms, you exist for less than a blink. Humans have existed for 0.002% of the universe's age. All of recorded history, 0.35%. You are watching a 4-hour movie, and you showed up 3 milliseconds before the credits. Yet here you are, conscious, aware, capable of understanding all of this. A collection of atoms arranged in such a way that they can comprehend the universe that created them. You are the universe becoming self-aware. Star matter waking up and studying stars. This is the paradox. You're insignificant in scale, but profound in meaning. The universe is vast and mostly empty, but it produced you. A species that went from hunting with stone tools to mapping the cosmic microwave background in 10 years. That has to mean something. Let's figure out what. Flying through every galaxy raises questions we still can't answer. Let's be honest about what we don't know. Why is there something instead of nothing? The Big Bang describes how the universe evolved from a hot, dense state, but it doesn't explain why that state existed in the first place. What caused the Big Bang? Did anything exist before it? Can before even be a meaningful concept without time? Some theories suggest our universe is one of many in a multiverse. Different universes with different physical constants, different laws of physics. Most would be dead universes, unable to form stars or atoms. We exist in one of the rare universes where conditions allow complexity. Not because we're special, because we couldn't exist anywhere else. This is the anthropic principle. We observe these particular physical constants because these are the only constants compatible with observers existing to do the observing. But that just pushes the question back. Why does the multiverse exist? What determines which physical laws are possible? Why these laws and not others? Or take dark matter. 85% of matter in the universe, and we have no idea what it is. Decades of experiments have failed to directly detect it. We've built detectors deep underground, shielded from cosmic rays. We've looked for dark matter particles colliding with normal matter. We've searched for evidence of dark matter annihilation producing gamma rays. Nothing. The universe is filled with invisible matter that refuses to reveal itself except through gravity. Maybe it's a particle we haven't discovered yet. Maybe it's something stranger, a different type of matter that barely interacts with ours. Maybe our understanding of gravity is incomplete and there's no dark matter at all, just modified gravitational laws at large scales. We don't know. And dark energy. Even worse. 68% of the universe is an unknown force pushing space apart with increasing intensity. We've measured its effects precisely. We know how strong it is. We know it's constant throughout space, but we have no idea what causes it. One possibility is vacuum energy. Quantum mechanics says empty space isn't truly empty. Virtual particles pop in and out of existence constantly, borrowing energy from the vacuum for brief moments before annihilating. This creates a baseline energy density in empty space. Maybe that's dark energy, but when physicists calculate what the vacuum energy should be, they get an answer 120 orders of magnitude larger than what we observe. The worst prediction in the history of physics. Another possibility is a new field, like the electromagnetic field or the Higgs field, that permeates all of space with a constant energy density. This field pushes space apart. Why does this field exist? What determines its properties? Nobody knows. The expansion itself raises questions. Space can expand faster than light. That seems to violate relativity. But relativity only limits motion through space. It says nothing about space itself. Space can do whatever it wants. Still feels wrong though, doesn't it? Like we're missing something fundamental about what space actually is, and those impossible early galaxies, Jade's GSZ40 and hundreds like it. They're real. The observations are solid, but they contradict our models of structure formation. Either the models are wrong, or the early universe was far stranger than we thought, or both. We've mapped the cosmic web. We've measured the CMB. We've catalogued 2 trillion galaxies, but we understand maybe 4% of what we're looking at. The rest, mystery, darkness, questions without answers. And maybe that's okay, because the questions matter as much as the answers. Let's talk about what comes next. Not for humanity, for the universe itself. Right now, we're in the stelliferous era, the age of stars. Galaxies shine, stars burn, planets orbit, black holes grow. This is the vibrant, energetic universe you flew through, but it won't last. Star formation is already declining. The universe hit peak star formation roughly 11 billion years ago when it was 3 billion years old. Since then, the rate has been dropping. Gas is getting used up. The universe is running out of raw material to build new stars. In 1 trillion years, the last star will form. After that, only existing stars remain, slowly burning through their fuel. Red dwarfs, the smallest and longest-lived stars, can burn for 10 trillion years. But eventually, even they'll die. They'll exhaust their hydrogen, cool down, and fade into black dwarfs. Cold, dark, stellar corpses drifting through space. By 100 trillion years, every star will be dead. The universe will go dark. No fusion anywhere, no light except the faint glow of cooling remnants and the occasional flash when objects collide. This is the degenerate era, the age of stellar corpses. Galaxies will evaporate, not instantly. Over incomprehensible time scales, stars orbit the galactic center, sometimes passing close to other stars. These gravitational encounters transfer energy. Some stars get flung out of the galaxy entirely, ejected into intergalactic space. Others lose energy and fall toward the central black hole. Over 10 to the 19th years, most stars in a galaxy will either be ejected or swallowed. Galaxies dissolve, spreading their dead stars across expanding voids. But remember, dark energy expansion is accelerating. Right now, the local group stays bound together. Gravity strong enough to resist expansion, but dark energy grows stronger as space expands. More space means more dark energy pushing outward. In 150 billion years, the Milky Way-Andromeda merger will be complete. Milkomeda will be isolated. Every other galaxy will have receded beyond our cosmic horizon, carried away by expansion faster than light can travel between them. Future astronomers will see nothing but their own galaxy surrounded by darkness. They'll calculate the universe's age and composition from the CMB, but they won't be able to verify their calculations because everything else will be gone. In 1032 years, protons decay, maybe. If they decay. We've never observed it happen, but some theories of physics predict it. If protons decay, then all normal matter eventually falls apart. Planets crumble, dead stars disintegrate. Black holes are left floating in an empty void. In 10 to the 100 years, even black holes die. Hawking radiation. Black holes emit particles and slowly lose mass. Larger black holes take longer to evaporate, but given enough time, all black holes eventually disappear in a final burst of radiation. After that, the heat death, maximum entropy. The universe reaches thermal equilibrium. No temperature differences exist anywhere, no energy gradients to drive any process, no stars, no planets, no black holes, just isolated particles spread across infinite space, so far apart they'll never interact with anything again. The universe becomes a dark, cold, empty expanse approaching absolute zero, unchanging for eternity. This is what expansion guarantees, not just the death of stars, the death of structure, the death of complexity, the death of the universe's ability to do anything interesting ever again, but that's 10 to the 100 years away, incomprehensibly far in the future. For now, right now, the universe is alive. You're back on Earth, standing under the night sky. You look up and see stars, a few thousand visible to your naked eye, maybe a faint smudge where the Milky Way's disk cuts across the sky. From down here, the universe looks static, peaceful, eternal. But now you know the truth. Those stars are moving, racing through space at hundreds of thousands of miles per hour, pulled by invisible matter toward massive attractors we can barely map. The galaxy you're in is colliding with another galaxy at 250 mph. Collision is 4 billion years away, but it's coming, inevitable. Written in the laws of gravity, the universe is expanding around you, space stretching, galaxies accelerating away, dark energy pushing everything apart with increasing force. The cosmic web is spreading, voids are growing. In the far future, almost nothing will remain visible, just darkness. Most of what you're looking at doesn't exist the way you think it does. 85% of matter is invisible, 68% of energy is unexplained. 4.9% of the universe is atoms, normal matter. Everything humanity has ever touched, measured, or understood fits in that 4.9%. You are standing on a rocky planet, orbiting a medium-sized star in a typical spiral galaxy, in a small galaxy group, in an average supercluster, in one tiny section of the observable universe, which itself is probably a minuscule fraction of the total universe. You are cosmically insignificant by any measure of scale, and yet you understand this, you mapped it. Humans went from believing Earth was the center of creation to discovering there are 2 trillion galaxies. From thinking the Milky Way was the entire universe to finding the cosmic web. From complete ignorance to mapping the CMB and calculating the universe's age, composition and fate. All in roughly 400 years. From Galileo's telescope to the James Webb Space Telescope. From seeing moons around Jupiter to seeing galaxies forming 300 million years after the Big Bang, 400 years of exponential discovery, you're part of the universe that became conscious. Star matter arranged into patterns complex enough to study stars. Atoms from dead supernova organized into brains capable of comprehending supernova. You're not separate from the cosmos. You're the cosmos examining itself. That's worth something. That means something. In a universe that's 95% empty, that will eventually die in heat death, that appears indifferent to whether anything exists at all, consciousness emerged. Complexity formed. Intelligence evolved. Understanding became possible. Maybe that's the answer. Not why the universe exists, but what we do while we're here. We're the universe's way of knowing itself. For this brief cosmic moment, this blink between the Big Bang and heat death, matter organized into you, into us, into a species capable of asking questions about existence. So, what do you do with that knowledge? Look up, study, explore, ask questions, build telescopes, launch spacecraft, map the cosmos, push the boundaries of what we can see and understand. Make the most of your impossibly brief moment as conscious matter in an ancient, vast, mysterious universe. Because one day, trillions of years from now, the last conscious being will have their final thought, and the universe will return to unconsciousness, eternal, empty, silent. But not yet. Before we end, there's one question we haven't addressed, the big one, the one that ties everything together. Why this? Why these physical constants? Why do electrons have the mass they have? Why is the speed of light exactly 186.0 miles per second? Why does gravity follow an inverse square law? Why is the cosmological constant so small that dark energy barely pushes space apart instead of ripping the universe apart immediately? Change any of these values by a tiny fraction and the universe doesn't work. Make gravity slightly stronger and stars collapse into black holes immediately. Make it slightly weaker and stars never form at all. Gas clouds just drift apart. Change the strong nuclear force and atomic nuclei either fly apart or collapse. Adjust the electromagnetic force and atoms become too large or too small for chemistry to create complex molecules. The universe sits in an incredibly narrow window where complexity is possible. Stars can form, elements can be created, planets can exist, life can emerge, consciousness can develop. This is called fine-tuning. The universe appears fine-tuned for life, or at least for complexity. Why? 3 possibilities. First, pure chance. There's only one universe and we got lucky. All the constants could have been anything, and they happen to land in the narrow range where we're possible. This feels unsatisfying but can't be ruled out. Coincidences happen. Second, the multiverse. There are countless universes, each with different physical constants. Most are dead, empty, boring. We exist in one of the rare universes where the constants allow complexity, because that's the only type of universe where observers could exist to notice. The anthropic principle. Again, we don't live in a special universe. We just can't live in the others. Third, design. Something set these constants deliberately. A creator, a simulation, a cosmic engineer. This raises more questions than it answers. Who designed the designer? What set their rules? But it's an option. We don't know. We have no way to know. We can't run the experiment. We can't create universes with different constants and see what happens. We're trapped in this one universe with these particular laws, trying to understand why from the inside. Maybe that's the final lesson. Some questions might not have answers we can reach. Not because we're not smart enough, not because we lack better instruments, but because the answers lie outside what any observer in any universe can possibly access. The universe revealed its structure to us. The cosmic web, the expansion, the dark matter, the CMB wall. We flew through all of it. From the Milky Way to the edge of observation, we saw everything light can show us. But some mysteries remain forever dark, hidden not by distance, but by the fundamental limits of knowledge itself. And we have to be okay with that, because the questions we can answer, they're extraordinary enough. You're still standing under the night sky, the same sky humans have looked at for hundreds of thousands of years. But you see it differently now. That faint band of light stretching overhead, the Milky Way, you've flown across its entire 100 light-year span. You've seen it from the outside. A magnificent spiral pinwheel of 400 billion stars. That smudge in Andromeda, our nearest large galactic neighbor. It looks small from here, barely visible without a telescope. But you've been there, you've seen its trillion stars, you know it's racing toward us for a collision billions of years away. The darkness between the stars, not empty, filled with dark matter, invisible scaffolding holding everything together. The space itself expanding, stretching, accelerating apart under dark energy's push. Every photon of starlight hitting your eye traveled through that expanding space. Some for years, some for millions of years, some for billions of years. Each photon carries a message from the past, a snapshot of how things were when that light began its journey. You're not looking at the universe, you're looking at history. The farther you look, the farther back you see. The night sky is a time machine, a museum, a record of cosmic evolution written in light. And somewhere out there, 46 billion light-years away in every direction, sits the wall. The cosmic microwave background, the oldest light, the edge of what we can see. Beyond it, the universe continues. How far? We'll never know, but it continues. 2 trillion galaxies in the observable universe, each containing millions to trillions of stars, each star potentially hosting planets. Some of those planets probably harbor life. Some of that life might be intelligent. Some of those intelligences might be looking at their night sky right now, asking the same questions we ask. Are we alone? Almost certainly not. The universe is too big, too old, too full of possibilities. Somewhere in some galaxy around some star, other conscious beings are mapping their cosmic web, calculating their expansion rate, wondering about their place in existence. But we will probably never meet them. Space is too vast. Expansion is too fast. The speed of light is too slow. We're islands in an expanding ocean, separated by distances that make communication nearly impossible. So, we look up, we study, we learn. We push the boundaries of knowledge as far as we can reach because that's what conscious matter does. That's what we're for. The universe spent 14 billion years creating you. Don't waste it. Now you know what's out there. You've flown through every galaxy. You've seen the cosmic web. You've touched the wall. Welcome home. That was the journey from the Milky Way to the cosmic microwave background and back. 100 light-years to 46 billion light-years. 1 galaxy to 2 trillion galaxies. 400 billion stars to more stars than atoms on Earth. We discovered we're not alone, not isolated. We're part of the local group flowing through Laniakea, riding cosmic currents toward massive attractors. We found the cosmic web, filaments and walls threading through enormous voids. We watched galaxies collide and merge. We flew backward through time and saw the universe being born. We learned that distance equals time, that expansion beats light speed, that most of the universe is invisible, that structure was predetermined by quantum fluctuations in the first fraction of a second, that the observable universe has an edge not because nothing exists beyond, but because light can't reach us from farther away. And we realized what we don't know, what dark matter is, what dark energy is, why physical constants have the values they have, why there's something instead of nothing, whether we're alone, what lies beyond the horizon. But we asked the questions. We built the telescopes, we mapped what we could reach, and we will keep pushing farther. Bigger instruments, better detectors, deeper observations. Each generation sees farther than the last. That's humanity's role. To explore, to understand, to be the universe studying itself. If this journey changed how you see the night sky, hit that subscribe button, share this with someone who needs a new perspective. Leave a comment about what surprised you most, and keep looking up. The universe is waiting. Thanks for flying through every galaxy with me. See you in the next one. You thought the cosmic web was the largest structure. You were wrong. In 1989, astronomers mapped the red shifts of thousands of galaxies in a slice of sky. They expected to find clusters scattered randomly. Instead, they found a wall. The CFA2 Great Wall, 500 million light-years long, 300 million light-years wide, 15 million light-years thick, a sheet of galaxies so vast it defied everything cosmologists thought possible about structure formation. Gravity can only build structures so large in 14 billion years. There's a theoretical limit. Pull matter together over cosmic time and you can create galaxy clusters, maybe superclusters, but walls spanning 500 million light-years, that requires time the universe hasn't had yet. There it is. And it's not alone. The Sloan Great Wall, 1.4 billion light-years long, the largest structure discovered in the 1990s and early 2000s. A filament of galaxies so enormous it spans roughly 1/60th of the observable universe's diameter. If you scaled the observable universe down to the size of Earth, the Sloan Great Wall would be 200 miles long. Then came the huge large quasar group, 2 quasars clustered together in a structure 4 billion light-years across. Quasars are the brightest objects in the universe, supermassive black holes actively feeding on matter and outshining entire galaxies. Finding 0 of them grouped together contradicted every model of cosmic structure. Formations this large shouldn't exist, period. But the universe wasn't done. The Hercules Corona Borealis Great Wall, discovered in 2013, 10 billion light-years long. 10 billion. That's more than 1/10 the diameter of the observable universe. It spans such a ridiculous distance that light takes 10 billion years to cross it. This structure began forming when the universe was only 4 billion years old, yet it somehow grew to cosmic scales. Here's why this breaks physics. The cosmological principle says the universe should look roughly the same in all directions at large scales. No preferred location, no special structures, homogeneous and isotropic, but these great walls violate that principle. They create a symmetry, direction, special regions where matter concentrated on scales that shouldn't be possible. Some cosmologists argue these aren't real structures, they're just line-of-sight effects. You're seeing galaxies and quasars that happen to align in your field of view, but aren't physically connected. Like seeing a constellation and thinking those stars are close together when actually they're at wildly different distances. But the statistical analysis says otherwise. These correlations are real. The galaxies in the Great Walls have similar red shifts, similar velocities, similar positions in three-dimensional space. They're gravitationally bound, or at least influenced by the same large-scale structures, which means the universe has features larger than our theories allow. The cosmic web isn't just filaments and nodes. It includes walls so massive they challenge our understanding of how structure forms from the smooth early universe revealed in the CMB. Remember those tiny temperature fluctuations in the CMB, 1 part in 100, 0? Those ripples supposedly seeded all structure. But ripples that small, growing under gravity for 14 billion years, can't produce walls 10 billion light-years long. The math doesn't work. The time isn't sufficient. Either we're missing something about how gravity works at cosmic scales, or the early universe was lumpier than the CMB indicates, or structure forms through mechanisms we haven't discovered yet. The Great Walls are real. They're there, mapped, measured, undeniable, and they're telling us our story is incomplete. Let's find out what else we're missing. Remember when I mentioned quasars? Let's talk about what they actually are, because they're the most violent, energetic, extreme objects in the universe, and they reveal something crucial about cosmic history. Quasar stands for quasi-stellar radio source. When astronomers first discovered them in the 1960s, they looked like stars, point sources of light, but their spectra were wrong. The light was redshifted by enormous amounts, indicating they were billions of light-years away. If they're billions of light-years away but still bright enough to see, they must be radiating incredible amounts of energy. How much energy? A single quasar can outshine its entire host galaxy, one point source brighter than 100 billion stars. That's not fusion. That's not any chemical or nuclear process. That's gravity. At the center of every quasar sits a supermassive black hole, millions to billions of times our star's mass. Matter spirals toward this black hole in an accretion disk, a swirling vortex of gas and dust orbiting at significant fractions of light speed. Friction heats the disk to millions of degrees. The material glows across all wavelengths. Visible light, X-rays, gamma rays. Some of the matter doesn't fall in. Instead, magnetic fields channel it into jets, narrow beams shooting perpendicular to the disk at 99% light speed, extending for thousands of light-years into space. The energy output is obscene. A typical quasar radiates as much energy per second as 1 trillion times our star's output. The most powerful quasars reach 100 trillion times our star. If you replaced our star with a quasar, Earth would vaporize instantly from the radiation. Now, here's the strange part. Quasars existed mostly in the early universe. When you look at distant galaxies at high redshifts, you find quasars everywhere. At redshift 6, 7, 8, corresponding to when the universe was less than 1 billion years old, quasars are common. But in the nearby universe, at low redshifts, they're rare, almost non-existent. Quasars were everywhere. Now they're gone. What happened? The supermassive black holes are still there. Every large galaxy has one. The Milky Way's central black hole masses 4 million times our star. Andromeda's black hole masses 100 million times our star. These black holes exist, but they're not actively feeding. They're dormant, quiet, dark. Quasars represent the growth phase. When supermassive black holes were young and actively consuming matter, the early universe was denser, more gas available. Black holes gorged themselves, powering quasars. Over billions of years, they consumed most of the available material. Star formation used up the gas. Galaxy mergers disrupted gas supplies. The feeding stopped. The quasars shut off. Today, supermassive black holes sit in galactic centers like sleeping giants. Occasionally, a star wanders too close and gets shredded by tidal forces. The black hole consumes the debris and briefly flares to life. Or a small galaxy merges with a larger one, funneling fresh gas towards the central black hole, reigniting activity for a few million years. But these events are rare. Most supermassive black holes stay dormant. When Andromeda collides with the Milky Way in 4 billion years, both central black holes will activate. Gas will funnel toward them during the collision. For a brief period, perhaps 10 to 100 million years, the merged galaxy will host an active galactic nucleus, maybe even a quasar. Then the gas will run out again, and the system will go dark. Quasars taught us that the early universe was chaotic, violent, energetic. Black holes grew rapidly, consuming matter and radiating enormous power. Now the universe is calmer, older. Most of the action already happened, but those sleeping black holes, they're waiting. In the far future, when galaxies collide and merge in the final stages before heat death, the black holes will wake one last time. One final burst of activity before eternal darkness. Speaking of black holes, let's talk about what happens when you have too many of them in one place. Everything in the universe rotates. Our star rotates. Earth rotates. The Milky Way rotates. Galaxy clusters rotate. Even superclusters show signs of net rotation. Spin is everywhere. But here's the question nobody can answer. Why? The Big Bang should have produced no net rotation. The early universe was almost perfectly smooth and symmetric. Tiny quantum fluctuations, yes, but no large-scale angular momentum. When something explodes from a point, you don't expect it to start spinning. You expect it to expand outward evenly in all directions. Yet, spin exists at every scale. And not just random spins. Patterns emerge. In 2011, researchers analyzed 70 zero-spiral galaxies. They found that galaxy spins aren't randomly oriented. Galaxies along cosmic filaments tend to spin with their rotation axis aligned with the filament, like beads on a string, all spinning around the string's length. This shouldn't happen. Galaxies form from collapsing gas clouds. Each collapse should produce random rotation direction, but the alignment suggests something in the large-scale structure influenced galaxy formation, imparting preferred spin directions. Then there's the quasar spin alignment. Quasars separated by billions of light-years show correlated spin axis. Their jets point in similar directions across cosmic distances. These quasars never interacted. They're causally disconnected. Light from one will never reach the other, yet their spins correlate. Some scientists propose cosmic strings as an explanation, hypothetical defects in space-time left over from the early universe. One-dimensional structures thinner than a proton, but stretching across cosmic distances. If cosmic strings existed, matter would collect along them. The strings could impart rotation to forming structures. But we've never detected cosmic strings directly. They remain theoretical. Another idea involves magnetic fields. The universe might have large-scale magnetic fields threading through the cosmic web. These fields could influence gas cloud collapse, creating preferred rotation directions. But where did these primordial magnetic fields come from? And why would they align across such enormous distances? Or maybe the answer is simpler: tidal forces. As structures form, neighboring structures pull on them gravitationally. This tidal pull can create torque, causing rotation. Over billions of years, these torques accumulate, but this explanation struggles to account for the observed correlations across disconnected regions. The rotation problem extends to the largest scales. Some researchers claim the entire universe has net rotation, that space-time itself spins around some axis. If true, this would violate the cosmological principle in a fundamental way. It would mean the universe has a preferred direction, an axis, a center. Most cosmologists doubt this. The evidence isn't strong enough. The measurements could be explained by local effects or systematic errors in data analysis. But it's not impossible. We already know the cosmological principle breaks down somewhat with the Great Walls. What if the universe does spin? What would that mean? Where would the angular momentum come from? Could the universe have formed from something rotating that transferred its spin to space-time itself? We don't know. Spin remains one of those cosmic mysteries hiding in plain sight. Everywhere you look, things are rotating. But why anything rotates at all? That question goes unanswered. Just add it to the list, right next to dark matter, dark energy, and impossible early galaxies. Light travels in straight lines, except when it doesn't. Einstein's general relativity predicts that mass warps spacetime. Imagine placing a bowling ball on a stretched rubber sheet. The ball creates a depression. Roll a marble past the bowling ball, and the marble's path curves as it moves through the depression. That's what massive objects do to spacetime. They curve it, and light follows that curvature. This means massive objects can act as lenses, gravitational lenses. A galaxy sitting between us and a more distant galaxy will bend the distant galaxy's light. The light curves around the foreground galaxy, sometimes splitting into multiple images, sometimes forming complete rings called Einstein rings. The effect is real. Astronomers use it constantly. The Hubble Space Telescope captured an image of galaxy cluster Abell 2218. The cluster's gravity is so strong it acts as a magnifying glass. Behind the cluster sits a distant galaxy, stretched and distorted into multiple arc-shaped images surrounding the cluster. The light from that distant galaxy traveled for billions of years, then got bent and amplified by the cluster's mass, allowing us to see a galaxy we'd otherwise be unable to detect. This is how we found some of the most distant galaxies. They're too faint to see directly. But place a massive galaxy cluster between us and the distant galaxy, and the cluster's gravity magnifies the distant galaxy's light, making it bright enough to observe. Natural cosmic telescopes, the universe providing its own magnification, but gravitational lensing reveals something else, something about dark matter. When you measure how much lensing occurs, you can calculate how much mass is doing the bending. The amount of bending tells you the mass. Simple physics. But when you count all the visible matter in galaxy clusters, all the stars and gas, the mass is too low. The visible matter can't produce the observed lensing. This is how the bullet cluster proved dark matter exists. Remember, two galaxy clusters collided. The visible galaxies passed through each other. The hot gas collided and piled up between the clusters. But when scientists mapped the gravitational lensing, they found most of the mass had passed through with the galaxies, not stayed with the gas. The mass creating the lensing is invisible. It doesn't interact with light, it doesn't emit radiation, it only interacts through gravity. Dark matter. The lensing maps its distribution, and what the maps show is clear. Every galaxy cluster sits inside an enormous halo of dark matter extending far beyond the visible galaxies. Some of the most bizarre lensing creates what astronomers call cosmic magnification. A foreground galaxy perfectly aligns with a background galaxy. The foreground galaxy's gravity creates an Einstein ring, a complete circle of light surrounding it. In a few rare cases, the alignment is so perfect you see multiple Einstein rings. Light from several background galaxies at different distances, all lensed into concentric rings by the same foreground object. The universe's largest lenses are the cosmic web filaments themselves. Light traveling from distant quasars gets weakly lensed by all the mass along the filament. Not enough to create multiple images, but enough to slightly brighten or dim the quasar depending on the alignment. This weak lensing has been used to map dark matter filaments that contain almost no visible galaxies. Space curves, light follows, and we see the invisible made visible through its gravitational shadow. Let's pause and connect what we've learned in the last few chapters. We discovered the Great Walls, structures billions of light-years long that shouldn't exist according to our models. The universe has features larger than physics, allows if we only consider 14 billion years of structure formation under gravity. We explored quasars, supermassive black holes powering the brightest objects in the universe by consuming matter. They were everywhere in the early universe, violent and energetic. Now they're mostly dormant, sleeping giants waiting for fresh gas to wake them. We found the spin mystery. Everything rotates, but we don't know why. Galaxies align their spins along cosmic filaments. Quasars, billions of light-years apart, show correlated rotation axis. The universe might even have net rotation, but the Big Bang shouldn't produce spin at all. The observable universe ends at the cosmic microwave background, 46 billion light-years away in every direction. Beyond that, we can't see. The universe was opaque before the CMB formed. Light couldn't travel. End of story. Or is it? The universe doesn't end at our horizon. Obviously, the CMB is just a wall where light stops reaching us from farther back in time, but space continues. Galaxies exist beyond our observable sphere. How far? That's where things get interesting. The universe has a minimum size. Measurements of cosmic curvature tell us the universe is flat to within 1% accuracy. Flatness implies the universe is either infinite or at least 400 times larger than the observable region. That's the lower bound. 400 times 93 billion light-years, roughly 37 trillion light-years across minimum. That's conservative. If the universe is truly flat, not just nearly flat, then it's infinite, literally infinite. No edge, no boundary, continuing forever in all directions. An infinite expanse of galaxies, stars and structure beyond what we can observe. If the universe is infinite, then every possible arrangement of matter exists somewhere. You exist in infinite copies, variations of you making different choices. Earths where history unfolded differently. Galaxies arranged in every possible configuration. Statistical certainty in an infinite sample, but even if the universe is finite, just 400 times larger than the observable region, that's still incomprehensibly vast. Our observable universe contains roughly 2 trillion galaxies. Multiply that by 400 cubed, that's 12.8 billion trillion galaxies in the minimum universe, most of them forever beyond our reach. Light from those distant regions will never reach us. Not because it's too far, because expansion carries those regions away faster than light can close the distance. The space between us and them stretches too rapidly. Those galaxies exist. They're real, but they're causally disconnected from us. We can't interact with them. We can't receive signals from them. They're in a different observable universe, seeing a different CMB sphere, observing a different set of galaxies. Now consider the multiverse hypothesis. Maybe our universe isn't unique. Maybe the Big Bang that created our universe is one of countless Big Bangs creating countless universes, each universe with potentially different physical constants, different laws of physics, different outcomes. Some versions of inflation theory suggest this is inevitable. Inflation created our universe by exponentially expanding a small region of space. But inflation doesn't necessarily stop everywhere at once. It could stop in some regions while continuing in others. Each stopped region becomes a universe. Each inflating region spawns more stopped regions, creating more universes. Eternal inflation, A multiverse, constantly birthing new universes forever. These other universes, if they exist, are completely separated from ours. Not just beyond our horizon, beyond any horizon. Disconnected spacetimes. No way to travel between them, no way to communicate, no way to detect their presence directly. Yet, they might be real. If inflation is correct, and most cosmologists think it is, then eternal inflation naturally produces a multiverse. Not speculation, not philosophy, a straightforward consequence of the physics we use to explain the universe we see. Other multiverse proposals exist. The many worlds interpretation of quantum mechanics. Every quantum event splits the universe into multiple branches, each branch representing a different outcome. You measured a particle's position. One branch of the universe saw it here, another branch saw it there. Both exist, both are real. Reality is a constantly branching tree of possibilities, all happening simultaneously in separated quantum states. Or the string theory landscape. String theory allows somewhere around 10 to the 500 different possible configurations of extra dimensions and vacuum states. Each configuration could represent a different universe with different physics. None of these multiverses are proven. They're consequences of theories that successfully explain other phenomena. Take the theory seriously, apply it consistently, and you get multiverses whether you want them or not. The universe we observe might be one island in an infinite archipelago, or it might be all there is. We don't know, can't know. The evidence lies beyond any possible observation. But the question matters because it shapes what universe even means. Most cosmologists accept the standard lambda CDM model, lambda representing dark energy, CDM meaning cold dark matter. The model works. It predicts the CMB structure. It explains expansion. It describes large-scale structure formation. It fits the data. But some scientists aren't satisfied. They point to the problems, the tensions, the unanswered questions, and they propose alternatives. MUND, modified Newtonian dynamics. What if there's no dark matter? What if gravity just works differently at very low accelerations? In regions where gravitational acceleration falls below a certain threshold, roughly 1/10,000,000th of Earth's surface gravity, gravity becomes stronger than Newton's inverse square law predicts. This would explain galaxy rotation curves without requiring dark matter. Stars at a galaxy's edge experience such weak gravitational acceleration that MUND's modified gravity takes over, making gravity stronger than expected, speeding up those outer stars to match observations. MUND works remarkably well for individual galaxies, but it struggles with galaxy clusters. The bullet cluster particularly challenges MUND because gravitational lensing shows mass separated from visible matter exactly where dark matter should be. Still, MUND refuses to die. New versions keep appearing, each attempting to explain more phenomena while maintaining MUND's core insight that gravity might behave differently at cosmic scales. Then there's the tired light hypothesis. What if redshift isn't from expansion? What if light loses energy as it travels through space, getting redder over cosmic distances without any space expansion at all? This would eliminate the need for dark energy. No accelerating expansion, just light getting tired. The problem? Tired light predicts observations that don't match reality. Supernovae should appear blurred at high redshifts if tired light is correct. They don't. The CMB temperature wouldn't have the right dependence on redshift. It does. Time dilation effects observed in distant supernovae match expansion but contradict tired light. Almost every test rules it out, but some researchers persist, proposing new mechanisms for how light might lose energy without causing the problematic predictions. More seriously, some cosmologists question whether the universe is actually homogeneous and isotropic. What if we're in a special location, a lower density region surrounded by higher density regions? This could make expansion appear to accelerate without requiring dark energy. Light from distant supernovae would traverse regions with different expansion rates, creating the illusion of cosmic acceleration. The problem: this violates the cosmological principle. It makes us special, central to a cosmic structure. And measurements of the CMB show The universe is remarkably uniform, no evidence for us being in an unusual void. Then there's varying speed of light theories. What if the speed of light was faster in the early universe? This could solve the horizon problem that inflation addresses. Distant regions of the early universe could have been in causal contact if light traveled faster back then, allowing them to reach similar temperatures and densities. Most physicists reject this. Varying light speed breaks too many fundamental principles. It conflicts with relativity. It complicates Maxwell's equations. It introduces more problems than it solves. But the proposals keep coming because the standard model, while successful, leaves 85% of matter unexplained and 68% of energy unexplained. When your model requires 95% of the universe to be things you can't detect directly, that invites skepticism. Most alternative theories fail when confronted with data. They make predictions that don't match observations. They explain one phenomenon but contradict others. The standard lambda CDM model remains dominant because it's the only framework that consistently fits everything we see. But that doesn't mean it's complete, just the best we have so far. The universe might still surprise us with revelations that force us to rethink everything again. Let's talk about what comes next, not billions of years in the future, the next few decades. What will we discover with the telescopes we're building right now? The James Webb Space Telescope launched in 2021. It's already revolutionized early galaxy studies, those impossible early galaxies like Jade's GS Zone 140. Webb found them. It can see in infrared, detecting light from the most distant galaxies stretched by expansion into wavelengths invisible to optical telescopes. But Webb is just the beginning. The Nancy Grace Roman Space Telescope launches in 2027, same size mirror as Hubble, but with a field of view 100 times larger. Roman will survey vast regions of sky, mapping billions of galaxies, measuring their positions and redshifts, revealing the cosmic web in unprecedented detail. It will detect thousands of exoplanets through gravitational microlensing, including Earth-sized worlds orbiting distant stars. And it will map dark matter distribution across the observable universe through weak gravitational lensing surveys. On the ground, the extremely large telescope in Chile will begin observations in 2028. A mirror 39 meters across. Adaptive optics to cancel atmospheric distortion. Resolution sharp enough to see details in distant galaxies. To study the atmospheres of exoplanets. To directly image planets around nearby stars. The square-kilometer array, a radio telescope spread across continents, will map neutral hydrogen throughout the universe. It will trace cosmic evolution by observing hydrogen at different redshifts, showing how gas collapsed into galaxies over billions of years. It might even detect radio signals from the cosmic dark ages, the period before the first stars formed. And there are proposals for even more ambitious instruments. Space-based gravitational wave detectors to observe black hole mergers throughout cosmic history. Neutrino observatories to finally detect the cosmic neutrino background. Telescopes on the far side of the moon, shielded from Earth's radio interference, capable of detecting the faint signals from the first stars igniting in the early universe. What will these instruments find? More impossible early galaxies, probably. Each new telescope with better sensitivity reveals galaxies at earlier times, pushing back the boundary of what we thought possible. We'll map dark matter more precisely. Better lensing surveys will reveal the detailed structure of dark matter filaments, showing exactly how visible matter traces dark matter distribution. Maybe we'll find anomalies, regions where dark matter behaves unexpectedly, clues to its particle nature. We might detect primordial gravitational waves, ripples in space-time from inflation itself encoded in the polarization pattern of the CMB. This would confirm inflation happened and measure its energy scale, one of the biggest discoveries in cosmology history. If it happens, we will study exoplanet atmospheres in detail. Webb is already doing this. Future telescopes will do it better. We'll detect atmospheric composition, temperature, weather patterns, and eventually we might find biosignatures, oxygen and methane in ratios suggesting biological activity, evidence of life beyond Earth. There's also the search for techno-signatures, not just radio signals, infrared waste heat from alien megastructures, unusual chemical compositions in exoplanet atmospheres suggesting industrial pollutants, laser pulses from interstellar communication attempts. As our telescopes improve, we're not just studying physics and chemistry, we're searching for intelligence. The next 50 years will answer questions we've asked for decades. Is dark matter a WIMP or something else? How exactly did the first galaxies form so quickly? Are we alone in the universe? Is the cosmological principle truly valid, or are there large-scale asymmetries? But here's what's certain. Every answered question will reveal 10 new questions. Every discovery will complicate the picture. Every breakthrough will show us how much more we don't know. The universe is 13.8 billion years old. Humans have studied it seriously for 400 years. We've mapped the cosmic web, measured expansion, found dark matter and dark energy, but we're still at the beginning, still learning the basics, still discovering fundamental things we missed. The journey isn't ending, it's accelerating, and what we find in the next century could dwarf everything we've learned so far. Keep watching the sky. The universe has barely started talking. You're back where you started, standing on Earth, looking up at the night sky. But now you see it completely differently. That faint band of light stretching overhead isn't just pretty. It's 100 light-years of structure, 400 billion stars bound together by gravity and wrapped in an invisible halo of dark matter 5 times more massive than everything visible. You're inside that halo right now, swimming in an ocean of invisible matter. Andromeda, that smudge barely visible in the constellation it's named after, is racing toward you at 250 mph. In 4 billion years, collision, both galaxies will shred each other and rebuild into something new. But you're also moving, pulled at 1.3 million miles per hour toward the Great Attractor, riding cosmic currents through Laniakea, following the channels carved by dark matter into the cosmic web. You're part of a river of galaxies flowing through space, and you never even knew it. The darkness between stars isn't empty. It's filled with neutrinos from the Big Bang, photons from the CMB redshifted into microwaves, dark energy pushing space apart, gravitational waves from distant black hole mergers passing through like ripples on a pond. Space is dense with invisible phenomena we're only beginning to detect. Every photon of starlight hitting your eye is ancient. Light from Proxima Centauri left 4 years ago. Light from stars in the Milky Way's center left 26 years ago. Light from Andromeda left 2.5 million years ago when our ancestors were just learning to use stone tools. Light from distant galaxies left billions of years ago when Earth didn't exist yet. You're not looking at the universe. You're looking at history. A time machine made of light. And beyond what you can see, the universe continues. 46 billion light-years to the CMB wall in every direction. Beyond that, possibly infinite. Trillions of galaxies forever beyond observation. Maybe a multiverse. Maybe infinite copies of you making different choices in parallel universes. Maybe something stranger we haven't imagined yet. The universe is 13.8 billion years old. It will continue for trillions of years more. Stars will die. Galaxies will merge. Eventually, everything will go dark and cold. Heat death, maximum entropy. The end of complexity. The end of change. But that's incomprehensibly far in the future. Right now, the universe is alive. Star formation happens. Galaxies collide and merge. Black holes grow. Structure evolves. The cosmic web spreads across space like a living thing. And here's what matters most. You're part of this, not separate from it. You are the universe. Star matter organized into consciousness. Atoms from dead supernovae arranged into patterns complex enough to understand supernovae. The cosmos studying itself. For 13.8 billion years, the universe was unconscious. Matter following physical laws. Gravity pulling gas into stars. Fusion creating elements. Supernovae scattering those elements through space. Planets forming, chemistry happening, complex molecules organizing. Then, roughly 3.5 billion years ago, on one small rocky planet orbiting an average star in a typical galaxy, something changed. Self-replicating molecules emerged. Life, evolution began. Complexity increased. Nervous systems developed. Brains formed. Consciousness emerged. The universe woke up. For the first time since the Big Bang, matter could observe the universe it inhabits, could ask questions, could discover physical laws, could map cosmic structure, could understand where it came from and where it's going. That's you. That's humanity. That's what we are. The universe's way of knowing itself. 400 years ago, we thought Earth was the center of everything. Now we know we're one planet orbiting one star in one galaxy among 2 trillion in the observable universe, which itself might be an infinitesimal fraction of the total universe. We moved from geocentrism to this, from believing we were the center of everything to realizing how small we truly are. And yet, in that humbling shift, we also moved from ignorance to understanding. We mapped the cosmos, measured the age of the universe, discovered dark matter and dark energy, traced the cosmic web and the Great Walls. We looked back 13.8 billion years to the very edge of what can be seen. That matters. It counts for something. Because in a universe that is 95% invisible, destined to fade into cold darkness, seemingly indifferent to whether consciousness exists at all, here we are, asking questions, finding answers, learning to understand. In a very real sense, the universe gave rise to you so it could become aware of itself. Don't waste that gift. Look up, feel wonder, ask better questions, chase deeper answers, keep exploring. The cosmos is vast, ancient and mysterious, and it's still waiting to be understood. The story of every galaxy is already written, but your own journey through the universe, that's only just beginning. Clear skies. And we saw gravitational lensing. Mass bends light. Galaxy clusters act as natural telescopes, magnifying distant galaxies we couldn't otherwise see. The lensing reveals dark matter's distribution, mapping the invisible halos surrounding every galaxy and cluster. Here's the pattern. The more we look, the more we find structures and phenomena that challenge our standard model of cosmology. Not enough to break it completely, but enough to suggest we're missing pieces. Dark matter makes up 85% of matter. We've mapped its distribution through lensing. We've measured its gravitational effects, but we still don't know what particles compose it. Dark energy makes up 68% of the universe's total energy. It's pushing space apart with increasing intensity. We've measured its effects precisely, but we have no idea what causes it. The Great Walls exceed theoretical size limits. Somehow, structure formed faster or more efficiently than our models predict. Early galaxies appear fully mature when they should still be forming. Jade's GS zone 140 and hundreds like it contradict our timeline for structure formation. Cosmic spin shows alignment across disconnected regions. Something created preferred rotation directions on scales that shouldn't maintain correlations. Each mystery stands alone, but together they point to something deeper. Our cosmological model works. It predicts the CMB. It explains expansion. It describes structure formation. But it's incomplete. It's like having a map that shows coastlines accurately but leaves the interior blank. The edges are right. The basic shape is correct, but critical details are missing. We're filling in those details. Better telescopes, more precise measurements, deeper observations. Each generation sees farther, measures more accurately, discovers new phenomena. The James Webb Space Telescope alone has revolutionized our understanding of early galaxy formation in just a few years. What will we find next? What else is hiding in the cosmos waiting to surprise us? Let's keep looking, because the universe has more secrets to reveal. Not everything in the universe stays where it formed. Some objects wander alone, unbound, traveling through the darkness between galaxies. Rogue planets, worlds ejected from their star systems through gravitational interactions. When a star system forms, multiple planets coalesce from the protoplanetary disk. Sometimes these planets interact. Close approaches, near collisions, gravitational slingshots. One planet gets flung outward, picking up enough velocity to escape the star's gravity entirely. Now that planet drifts through interstellar space. No star to orbit, no light to warm it. If the planet had an atmosphere, it freezes. Any liquid water becomes ice. The surface temperature drops to near absolute zero. These worlds sail through the darkness. Invisible, detectable, only if they happen to pass in front of a background star and cause a brief gravitational microlensing event. Estimates suggest there might be billions of rogue planets in the Milky Way, possibly more rogue planets than stars. An entire population of wandering worlds, most of which we'll never detect because they emit no light and rarely pass directly between us and distant stars. Some could be massive Jupiter-sized worlds that almost became stars themselves but got ejected before accumulating enough mass. Others could be Earth-like rocky worlds that once hosted liquid water oceans before losing their star. Their oceans would freeze. But beneath the ice, radioactive decay in the planet's core could maintain subsurface liquid water for billions of years. Potentially habitable environments in isolated worlds floating through the void. Then there are rogue stars. Stars ejected from galaxies by close encounters with supermassive black holes or by three-body interactions in dense star clusters. These stars shoot out of their host galaxies at hundreds of kilometers per second, fast enough to escape galactic gravity. They're out there right now, stars traveling through intergalactic space alone between galaxy clusters. If planets orbit these rogue stars, those planets experience a strange sky. No galactic disk overhead, no Milky Way band, just a few thousand nearby stars from their own system and distant fuzzy patches where other galaxies shine billions of light-years away. The most extreme rogues are hypervelocity stars, stars moving so fast they'll escape the Milky Way entirely. Some exceed 10 kilometers. At that speed, you could travel from Earth to our star in less than 2 days. How do stars reach these velocities? Close encounters with the central black hole. A binary star system wanders too close to Sagittarius A, our galaxy's supermassive black hole. The black hole's gravity tears the binary apart. One star falls toward the black hole, transferring its momentum to the other star, which gets flung outward like a slingshot. That ejected star carries enough velocity to leave the galaxy. Hundreds of hypervelocity stars have been identified. Most are heading out of the Milky Way, never to return. In a few million years, they'll be intergalactic travelers moving through the space between galaxies with nothing but dark matter and the occasional atom of hydrogen for company. And it's not just planets and stars. Entire galaxies can go rogue. Small dwarf galaxies sometimes get ejected from galaxy clusters through gravitational interactions. These orphan galaxies drift through intergalactic voids, isolated, slowly exhausting their gas and ending star formation. The universe isn't just the structures we map, it's also the wanderers, the ejected, the rogues. Objects that broke free from their gravitational homes and now travel alone through cosmic darkness. Silent, isolated, moving through space for billions of years with no destination, no neighbors, no purpose except to exist. And most of them we'll never see. You know about the cosmic microwave background, the oldest light in the universe. But there's something even older, something we've never directly detected but know must exist, the cosmic neutrino background. 1 second after the Big Bang, the universe was hot enough that neutrinos interacted frequently with other particles, but as expansion cooled everything down, neutrinos decoupled from matter. They stopped interacting. From that moment forward, roughly 1 second after the Big Bang, neutrinos traveled freely through space. Those neutrinos are still out there everywhere, filling the universe like an invisible ocean. The cosmic neutrino background, roughly 340 neutrinos per cubic centimeter of space. That's about 500 trillion neutrinos passing through your body every second from all directions. You don't feel them. Neutrinos barely interact with normal matter. A neutrino can pass through a light year of lead without hitting anything. That's why detecting them is nearly impossible. They're ghosts, present but intangible. The CMB formed 380. 0 years after the Big Bang, when photons decoupled from matter. The cosmic neutrino background formed 1 second after the Big Bang when neutrinos decoupled. This makes the neutrino background roughly 380 times older in terms of decoupling time. If we could detect the cosmic neutrino background, we'd see the universe as it was 1 second after creation, not 380 years. 1 second. The CMB shows us the universe in its infancy. The neutrino background would show us the universe in its first moments. What information does it carry? Everything. The temperature distribution 1 second after the Big Bang, the density fluctuations, the formation of the first atomic nuclei, the ratio of matter to antimatter. Neutrinos witnessed all of it and carry that information encoded in their distribution and energy spectrum, but detecting them requires technology we don't have yet. The CMB is relatively easy to detect. Photons interact with antennas and telescopes. Build a sensitive instrument, point it at the sky, and you see the CMB. But neutrinos, they pass through your detector as easily as they pass through everything else. Current neutrino detectors work by placing enormous tanks of water or other target material underground and waiting for the rare occasion when a neutrino actually hits an atom. Those detectors can detect high-energy neutrinos from supernovae or from our star. But the cosmic neutrino background consists of low-energy neutrinos moving slowly through space. Detecting them would require detectors far more sensitive than anything we've built. Theoretical proposals exist. Massive detector arrays, kilometers of target material, ultra-cold environments to reduce noise. Even then, detecting a single cosmic neutrino would be extraordinary. Mapping the cosmic neutrino background in detail, that's centuries away, maybe longer. But it's there, proven mathematically. The Big Bang produced these neutrinos. Physics demands they exist, and unlike the CMB, which has been disturbed by intervening matter-absorbing and re-emitting photons along the line of sight, the cosmic neutrino background is pristine, unchanged, perfect. A snapshot of the universe 1 second after creation, preserved in an invisible sea of particles too shy to interact with anything. One day, we'll detect it, we'll map it, and we'll see further back in time than we've ever seen before. We'll witness the birth of the universe with unprecedented clarity. But not today. For now, the neutrino background remains one more invisible layer of cosmic architecture, present but unreachable.